Hello?
Yes, sir, we can hear you.
Yeah, we can hear you.
Amit will start sharing.
Amik,
Can you see the
The
shared
screen
screen?
is shared.
yeah, I can see the screen, but can you see me or can you listen to me?
Yes, sir, we can listen to you.
Okay, then let's start.
Yeah.
Then let's start.
So thank you everyone for joining us with today. Sorry for the technical issue. There was a small delay for it. We are extremely sorry for it. So today we have Professor Bimal Kumar Roy from ISA Kolkata. Let me give you a brief introduction about him. He completed his PhD from University of Waterloo in 1982. He was a director of ISA Kolkata from 2010 to 2015 and currently the head of RC Bose Center for Cryptography and Security at ISA Kolkata. He was also the advisor of Secure Wireless Communication Special Protection Group, Government of India, and currently the chairman of Indo-French Center for Applied Mathematics, Department of Science and Technology, Government of India. Professor Bimal Kumar Roy is also the recipient of Padma Shri in 2015. So today he is going to deliver a talk on issues in e-voting, which will take us through the challenges faced in e-voting and how to deal with them. Not only this is interesting, it is also quite relevant in the present situation where we are having elections, but we are stuck at home due to COVID situation. So before we begin, just a small instruction, please use the chat box for your questions and we will take up with the professor at the appropriate times. Hope you all enjoy the talk. Professor.
Okay, thank you, Amik. And
Yes,
I'm
sir.
sorry that we got into all this technical mess. Me being basically mathematician, so unprofessional with the technicalities, I often
Yes,
get
sir,
into
that's not a problem.
problem. And I personally don't like to talk over this internet. I prefer, meeting the students and looking at their body language, and also, I moderate my talk also as I go along. But that's not possible here. So let me just start my talk, and first let me talk about the different issues in e-voting, step by step. And I'll start giving some kind of solution. Maybe I'll start from the end and come to the initial part at the end.
Yes, sir.
So if you think of many of you are probably not voters, or maybe I think all of you are voters. All of you have crossed age 18, right?
Not everyone. There are some 8th graders and 9th graders also. Currently, they have not.
Then voted. So you look into our voting procedure. So we have an election ID card. Okay, we go to a booth. There is a machine there, and there is a polling officer. Polling officer has a list of all the valid voters for that booth, along with their a copy of that voter ID printed. So it has got your picture, it has got your signature or thumb impression. So the polling officer has got a copy of your picture and also your either signature or thumb impression. So what the polling officer will first ask you to show your voter ID. So that's what you show. Then he looks at my face and tries to see whether the picture that he has got in his record, the picture that is on that voter ID, and the face of it that he's observing, whether these three are the same or not. He makes his own decision, and if he's satisfied, then he says that yes, I'm the right voter. So he allows me to vote. But before he allows me to vote, there's attendance registered there list. You are asked to either sign or you are asked to put your thumb impression if you cannot sign. And then again, he will verify with the signature that he has got with him, a copy of my signature or your signature. You will verify the signature you're putting there, whether these two are matching, then is allowed. The next one is if I cannot write, I cannot put signature. There are many Indians like that. So he will ask you to just put your thumb impression there. And once you put the thumb impression, he tries to match the thumb impression in his document and the thumb impression that the voter is putting at that point of time, and it just matches, and that is going to satisfy him that I am the right person. So this is the first, and the first question here is that now matching this photos by eye inspection, matching the signatures by eye inspection. Well, there could be some error, could be a lot of error, but matching the finger thumb impression by visually by your vision is practically impossible. Okay, so when the polling officer makes a judgment that you are the right person, there is a scope of lot of error there. And you know, in India, it happens. Well, I don't take pride of that. Impersonation or false voting do take place. Say a person votes for somebody else's vote, and this is not very uncommon. So this is what I call impersonation. And in our voting process, impersonation is possible. It's not that I'm telling that it's happening all the time, but it is possible. I could impersonate some other voter and go and vote on his behalf. This is number one. Number two, then he allows me to vote. So I go to the EVM, that electronic voting machine, and there will be symbols, and I press the button near the symbol of my choice, and I press it. And then what they do, they will just, it's a VVPAT machine, it will just print the symbol on which I have casted my vote, and you see that picture on the piece of paper, and you see that this is the symbol that where I voted. So you are happy, and then this piece of paper drops down, and in the EVM memory, my vote goes and stored there. Okay, this is what you see, and looking at the VPAT machine, that printout of that symbol and where I voted, we try to match, and we get satisfied that yes, my vote is recorded. This is my next step. The third step is after the voting is done, this EVM is put under some lock and key in some secure place, and the counting happens after many days. Okay, after many days, 3, 4, 5, 7, some is in a year election. Election starts on 28th of October. The counting is on 10th of November. So 13 days, this EVMs are lying there in some custody. And then on the 10th of November, they will start counting. That means basically they will try to see the vote count in every machine. So this is the second step. And this is where I remember Honorable Chief Minister of Delhi, Mr. Arvind Kejriwal, he objected that in this period, the government has done some malified actions, so they changed some votes. So some mischief goes on, and the memory is changed. So the vote count you see in the counting stage is not the same as the votes were actually stored. Some change, some hulla gulla on the memory has taken place. And he challenged the Election Commission to prove that they didn't do it. So they actually put a committee, blah, blah, blah. But it didn't quite satisfy Arvind Kejriwal. He walked out of that process. Okay, and then this is his concern. And then the last thing that is my concern, the issue of privacy. I'll tell you an example which I faced in our West Bengal voting last time. A student of mine lives in some deep interior village in some district in West Bengal. And now, when the counting are done, so people know the voting pattern for every EVM. That means for every booth. Now, what is a booth? It's basically a small physical area. So if a village, if there's some large village, they have this hamlet concept, the para concept, or the village is small, the village itself. In Calcutta city, if you have these housing complexes, then one housing complex votes in the same EVM. So what does that mean? This means that everybody would know that how people voted in this physical region where the EVM represents. That's what I feel is a breach of privacy. And it so happened that I remember this in Calcutta, some housing estate, the vote didn't go in favor of the ruling party, or the ruling party person actually won the election because there are so many booths comprised of one constituency. So he won, but then there was some water problem. So these people went to the local MLA that we have to resolve our water problem, and immediately says, "You didn't vote for me, so why should I work for you?" Now, this is a shame for democracy, but at the same time, this wouldn't have happened if this EVM level vote count was not available. There's no business of knowing how a particular small community voted. So this is what I call breach of privacy. So these are the issues. And so what I would put my steps as a fair, scientific proven voting. Number one, the person must vote his or her own vote. No impersonation. Number one. Number two, I must ensure that my vote is stored there. So the machine has stored my vote, and I want to be sure of it. And VPAT doesn't quite satisfy me. Next step, you have to make sure that the vote stored doesn't get hampered in this process when the is lying idle. Okay, so they'll store. I cast my own vote. What I cast is actually stored, and what I stored is actually tallied or counted. So this is the process, and at the end, I don't want to have any privacy issue about the particular physical location of particular booth. So nobody would know how a particular booth voted. Okay, so these are the issues. So I'll start with the easiest one, the last one. How can I get rid of this privacy issue? That all I want to ensure that the voting pattern in a particular booth, which basically represents a very small physically geographical location, people should not know how they voted. So I just give a very small example. Suppose I have got two machines. Okay, so I've got two candidates, two machines and only two candidates, candidate A and candidate B. So maybe in candidate A got 200 votes, candidate B got 500 votes. In the next machine, candidate A got 400 votes and candidate 2 got say 200 votes. Total number of votes acquired by A is 200 plus 400, 600. And total number of votes acquired by candidate B is 500 plus 200, 700. So I want to only publish the 600 and 700 against these candidates, not in individual machines. Then what do? I have a very simple solution. So at the counting stage, I hope all of you know what is a random number. I generate a random number. Okay, say I generate an R. I send this random number to both the machines. In the first machine, the number of votes A got, say it was 200, I will add that random number. So the random number is 300. So this will add 200 plus 300, which is 500. So the first machine will publish this sum, the actual vote acquired plus the random number. So 200 plus 500. For the second machine, I'll subtract the random number from the count there. So it has actually got 400 votes. I subtract 300, so it will say 100 votes. The first machine will show 500, second machine will show 100. I'll add these two. 500 plus 100, so this is 600. It's the same as it used to be if I didn't do this random number business. It was 200 and 400, it would have been 600. But I'm not publishing 200 and 400. Instead, I'm publishing 200 plus the random number R publishing 400 minus a random number R. And I'm adding them up, so I'll get the same sum. But since the number is randomly chosen, well, this is the theory of how to choose random numbers. It is practically impossible to guess or to estimate what was the actual count in every machine. So from this, if I don't know the random number, say 300, so you publish 200 plus 300, 500. From this 500, you don't know that the actual value was 200. So if I do this one, then I can do another random number for the second candidate. So the machines will, first machine will publish the number of votes acquired plus a random number. Second machine will do number of votes there minus a random number. Now I can do a simple exercise to all of you. Now you can just use the random numbers in such a way that if there are multiple candidates and multiple number of EVMs, you can actually design an algorithm which is going to give you the sum of the votes obtained by each of the candidates without revealing the number of votes one candidate got in a particular booth. So I hope this is clear. So for the two machines and two candidates, but this you can immediately generalize to any number of machines, any number of candidates. So that's an exercise for you. And this is what is called very generally in this domain, multi-party, secured multi-party computation. But this I think you can do it. So I leave it up to you. And if you do get a solution, do send me an email. So Amikraj Behara has my email. So you can share my email address, all of them. And if any of you can find a solution, just send me an email. I'll be very happy to evaluate a solution. I hope you understand the issue there. Okay, so nobody would know the voting pattern in any of these EVMs or any booth, but the sum will be computed very securely, from which this voting pattern at booth level cannot be reconstructed or computed back. So I have given a solution for two candidates and for two machines, a very simple randomization technique, and you have to generalize it to any number of candidates, any number of machines. So I told you I'll start from the end. The last problem is resolved by this. Okay, then I come to the actual voting. Okay, I will just talk about, there is a one slide that I'm going to use, and I don't know, Amik,
Yes, sir.
do they know a group or cyclic group?
So, some
Audience?
of them may know a cyclic group.
Okay, so I need that little algebra. If
Yes,
you
maybe
don't,
a bit of the definition of cyclic group would suffice.
yeah, so well, so if it is the, shall I start defining a group and then cyclic group, or just okay?
So,
I'll talk about. So I'll talk about a group means a bunch of elements and an operation. You think of the real numbers and say multiplication. Okay. So this is a group, meaning that we have some group postulates, they are satisfied. Okay, and I'll talk about finite groups, so not real numbers. So my context will be all finite group. And cyclic group means that there is something called a generator, and all the elements are some power of that generator. So there's one or maybe at least one very special element in that group, and every other element can be written as a power of that particular element, which I call the generator. So any element would be the group will have an element I call generator G, and every other element will be some G power A, some G power some A. Okay, so this is your cyclic group, and there are algorithms to find generator, which is not a very trivial thing. The algorithms for finding generators, and we handle with very, very large groups, not small groups, very, very large groups. So this is, and I'll start with a group, very large group, and I'll choose two generators, G1 and G2. And I'll talk about one very strong mathematical result here, computational mathematical result, logarithm. In high school, you study logarithm. So if it is a if in the domain of the cyclic group, then every element B, so if you think of element B is going to be G power A. So then I can define a logarithm of B to the base of G. If B is equal to G power A, then we can say log of B to the base J is going to be A. Okay, that's what we call discrete logarithm. And since it's a cyclic group, there exists an A, so that every element B is G power of that A. Now, what is the discrete logarithm problem? That in a large cyclic group, if you know the generator G, if you know the element A, is a B, finding logarithm of B to the base of G. That means that number A, that B is G power A, finding that A. Given a B, finding that A. This is, as of today, is a very hard problem. Meaning that for most of the cyclic groups, unless a few trivial ones, you don't have a good algorithm to compute the discrete logarithm. So this is called a computation hard problem. So we, in this community, we assume that this discrete log problem is computationally hard. Some groups are very toy-like, in which you can do it, but we normally choose a group where this problem is hard. That means if you know an element and if you know the generator G in the cyclic group, then logarithm of that element to the base G is not easily computable. That's what is a result as of today. But tomorrow one of you can come up with a very nice algorithm. But it doesn't say that there doesn't exist one. As of today, we don't know. In fact, I can just mention you one relevant result here. Till 2001, we didn't know really how to find a prime number. If I tell you whether this number is prime, you basically ended up dividing that number by smaller prime numbers and go up to the square root of that number. Suppose I tell you 127379, is it a prime number? We used to actually start dividing this by 2, then by 3, then by 5, then by 7, and so on and so forth. And if none of them divide this and I go up to square root of that number, none of them divides, then I say this is a prime number. If n is very large, square root of n is very large, and this test will never finish. Okay, so till 2001, we really had no good way of finding prime numbers, and people thought this is a very difficult problem. Okay, so we used to have a lot of algorithms which are probabilistic. So this means I have an algorithm. So if you give me a large number, I can tell whether this is prime, but with certain probability. The probability could be very close to 1, but the certain probability is not probability 1. And then so till 2000, we believed that this is a very hard problem, getting a prime number. But this phenomenal result by 2 students and their supervisor at IIT Kanpur, 2 BTech students, Nitin Saxena and Neeraj Kayal, and their advisor Manindra Agarwal. They found an algorithm where they showed that they can actually do it of the order of log n cube. Number is n, it's not square root of n, log n cube. They found an algorithm. This is called AKS algorithm, Agarwal, Kayal, and Saxena. And so we know that yes, this is not a hard problem. We can find prime numbers. And log n power cube is pretty manageable thing. Square root of n is much larger. So maybe tomorrow somebody may come up with some bright idea of computing the discrete log, and then this solution will fall through. I mean, fall apart. So at this point, I'm assuming that given a cyclic group, given a generator, and if I give an element in that group, finding the logarithm of that element to the base of that particular generator is computationally very hard. That means for all practical purpose, we cannot compute it. That's the basis of my entire rest of my work. Okay, so I'll tell you what I mean by vote. Again, I'll just give an example here. There are only 2 candidates, and you can generalize it to many candidates. Only the mathematics becomes more complicated. The idea remains the same. Let me assume only 2 candidates. I vote 0 or 1. 0 for the first candidate and 1 for the second candidate. Okay, and so when I say vote VI, VI is either 0 or 1. And I have chosen a group, very large group, and I have chosen 2 generators, G1 and G2. Okay, and I make it public. So people would know that the election commission has adopted this group with these generators. So nothing to hide here. So everyone knows G1 and G2. Now, what I would do now, so when you go to vote, you have to choose a random number. Random number, say RI, ith person. I can just forget the suffix now I, because so one person will choose a random number R. So you could just pick up any number you like, or there could be a random generator in the polling booth, using which you can generate your number. Okay, so this number is chosen by the voter. Okay, so you enter your vote and you enter your random number. The machine will accept this RI and VI. And then the machine will compute G1 power the random number or RI. That's what I call UI. And it will also compute G2 power RI plus VI, which is I call VI. So what the machine does, once you enter your R, once you enter your vote 0 or 1, machine will immediately compute G1 power R and G2 power R plus your vote V. And this will make public. So I'll talk about later on how do I make it public. So there is a notion called blockchain, or it could be hash chain. I'll come later on. So but this will be put into a public domain. So anybody who have an access to this value UI and VI. But then the question comes from UI. Can I guess VI? That is the notion of privacy. I'm publishing UI and VI. Now, can anyone compute VI from there? If somebody can compute, then that means my vote is exposed. My vote is not going to be private. But if you look into this very carefully, these 2 questions, from UI and VI, you have to find out that VI, small VI, your vote, it amounts to solving the discrete block problem. So if you cannot solve the discrete problem, hopefully you cannot compute this VI. And as long as the discrete block problem is difficult or hard, then exposing UI and VI doesn't expose your vote. And UI, VI, I put on the public domain. And what the machine does not quite record all the RIs and VIs, but it goes on accumulating. So first you put your RI and VI, it takes. Next person comes, puts inputs his or her RI and VI, then it will just add the 2 Rs. The R already available R and the V's. So it goes accumulating. At the end of the voting process, the machine will have in its memory summation RI and summation RI plus summation VI. Okay. So at the counting stage, the machine will output the summation RI and summation RI plus VI. And then you can subtract summation RI plus VI minus summation RI. This will give you summation VI. And that is the number of votes the second candidate got. And number of votes the first candidate got is just by subtraction. Okay. And now, how do I make it people confident that nothing things are done correctly? The machine did not make any foul play. This is my next lines. The machine is going to publish summation RI plus summation VI. Now the machine is going to public for each voter UI and capital VI. Now anybody from that public domain can compute the product of all these UIs. You have these UIs, you can compute this product of these UIs. You can compute the product of all these VIs. Okay. So UI is actually going to be your G1 to the power summation RI. The machine at the counting stage is giving you summation RI. You have the G1. So you can compute yourself G1 power summation RI. And you are also computing product of this UI. These 2 must match. Same to the second one. Machine is giving you summation Ri plus Vi. So you can compute G2 power summation Ri plus Vi. And you can also multiply all these VIs, product all these VIs, and these two must tally. So anybody who is interested to ensure that this is a fair process, nothing illegal thing happened here or immoral thing happened here. So anybody can verify this, publicly verifiable. Okay, and this all depends on the hardness of discrete logarithm problem. Okay, now the thing is, how do I make this public? This UI and VI, and I have to make sure that nobody is going to change these UIs and VIs. If UIs and VIs are changed, then all the games become very unfair. So once the machine computes UIs and VIs and puts in public domain, it should be immutable. And I have no time to talk about the blockchain technology. Blockchain technology is something you can store data, where data is immutable. That means if you try to change even one bit in the data, the machine will give you a signal that something has changed. So now that's another 1 or 2 hour lecture to explain about the blockchain. So what we may recommend that all these UIs and VIs are put into a blockchain. So this means that if anybody tries to change this UI and VI, the machine will immediately identify. So UI and VI. So UI and VIs are not, these are immutable. So they can be changed, and this becomes publicly verifiable. All this voting process, what has happened, it's not only the normally what you do, there will be the candidates and then some press sitting while the counting is going on, they only verify. But here by this, anybody can verify from anywhere in the world that this vote has been done fairly. This is, but still I find some issue with this one. There could be some false voting here. How do I do the false voting? Now, since this I'm working in a group, if I could get a number of RIs, random number choice from the group, if they add up to 0 in their group, okay, then what I can do, I can generate false votes with those RIs, and I put my choice of vote there. I fix my VI equal to 0 or 1. If I'm favoring the second candidate, I put all VIs 1. Okay, then the summation Ri and summation Ri plus Vi. Okay, this Vi actually changes, but the Ris don't change. So when you do the public verification, nobody can understand that. So if I can actually get a bunch of Ris which add up to 0, so using those Ris, I can create false votes. Well, I have to have the access to the machine, but somebody has the access to the machine itself can actually generate false votes and can favor any of the candidates. So the issue is that summation Ri is 0. So when I choose this Ris, whether I can generate things like summation Ri equal to 0. Okay, so there what we try to do, when you choose these Ris, we want to make sure that none of the subsets are really adding up to 0. That's again a cumbersome process, but we have to ensure that. So I'm choosing Ri, and I choose Ri. We want to make sure that those Ris don't add up to 0. If they add up to 0, then there's a problem. But we have a more secure way of handling that one. Again, that gets into some more mathematics. But this is the way I could put some false votes, and we have worked out a process by which I can prevent this one. That if somebody wants to put a false vote, trying to choose summation Ri 0, we have a way to identify that. So this is the way we can actually stop this false voting. Okay, now comes I come to the first stage, and I want to ensure that my vote has been stored. Okay, so what I can do, so we give a scope of auditing your vote. So you first vote. Okay, you vote. You vote your you put your R and V, and the machine is supposed to give you back U and UI and capital VI, and you can verify that these are computed correctly. Okay, now here where I don't have much time to explain that theoretically. There's something called a new mathematical probability game called zero knowledge proof. Okay, so we actually use a zero knowledge proof here. I want to verify that my vote has been stored there. Now, getting into more formulas here will make you more complicated. So I'll give an idea of what is meant by zero knowledge proof. So I have a very nice story about that. Now, okay. My first story is very intriguing. Suppose I have got two nieces. Actually, I do have two nieces, and when they're young, if I want to get one gift for one niece, I have to get the identical gift for the other niece. Otherwise, they get very upset. So I decided to give them, maybe buy some 2 pens and give to them, but they have to be identical. And now the problem is, you assume that I am blind. I'm blind, so I cannot see. So I ask Amik, can you get me 2 identical pens? Okay, so Amik gets me 2 identical pens. I trust him. But Amik wants to prove that he has got 2 identical pens. It's again not the question of distrusting. So I trust Amik. I don't know, Amik, I'm fine. I trust you. You must have got 2 identical pens. But Amik still wants to prove to me that he has got 2 identical pens. Okay. So he designs a game now. He says, okay, let's put an arbitrator. Arvindan, is it? The other person, Arvindan, right? Who has is it Arvindan, Amik? Who was communicating?
Yes, Aniruddhan.
Aniruddhan. Okay, so he said, okay, let's put an arbitrator and let them play a game. Okay, this game is so nice. Just if I could see you in person, and I could actually make the game happen in a talk. So Amik says, you hold these 2 pens in your 2 hands. Okay, so I hold the 2 pens in my 2 hands. Can you see me? Can you see me? I hold my 2 pens.
Yes, sir.
Yes, sir.
You can see, but these 2 are not identical. Okay, so I take these 2, and then Amik says, take your 2 hands at your back. Okay, I take at my back. Now Anirudh cannot see, but then Amik says, you may interchange your hands or you may not. It's like this. My left hand has this pen, the right hand has got this stapler. Okay, so I take it at the back and I bring it in the front. Again, in the left hand, I have got the pen, and right hand, I have got the stapler. So Aniruddhan would be able to say that, yes, sir, you did not interchange your hands. But if I did interchange, okay, now then the stapler comes to my left hand and the pen comes to my right hand. And then immediately Aniruddhan will understand that I have interchanged my hands. And it says, yes, sir, you have interchanged your hands. So if they were not identical, Aniruddhan will be correct all the times, right? But if they're identical, now think what is going to happen to Aniruddhan is in trouble. If these 2 are identical pens, identical objects, then whether I interchange hands or not, how does Aniruddhan guess? He has to just make a guess. Okay, he may be correct or wrong, he just make a wild guess. So if I play this game a number of times, if Aniruddhan does mistake, first time he does a mistake, that means I'm pretty sure these 2 are identical. Because in case of they are distinct, Aniruddhan has no chance of making any mistake. He will make a mistake only if these 2 are identical. So Amik says, you play the game between you and Aniruddhan, and we play the game maybe 5-10 times, depending on how much error do I allow. So say play 10 times, and you stop as soon as he does the first mistake. If Aniruddhan does the first mistake, I know that they are identical. Otherwise, you continue this game number of times, and if it's always correct, say 10-12 times, it's pretty sure that these 2 are not identical. So this is a very peculiar probabilistic game, and this is what is called a zero knowledge game, proving something. Okay, I'm proving it's identical, even I cannot see this. So we use this this specific idea of the zero knowledge proof. If somebody interested, I can send you the exact zero knowledge game I applied for this one. If what is involved mathematics, so I can send you the actual write up on this. So what we propose that when you vote, okay, your RI and VI, then we actually design a zero knowledge game between the machine and you. So you play the game with the machine, and you can be sure that the machine has stored your vote correctly. We'll be sure. So as I say, now I don't want to put all these things that involve mathematics, long formulas. But if somebody interested, I can send you the document of the zero knowledge proof. So actually use the zero knowledge game to ensure that that vote is actually stored the way I voted. So when I leave the voting machine, I'm absolutely sure that my vote has been stored. That's the zero knowledge game. Okay, and then I talked about how do I store the votes. So people can actually even see. I'll tell you some issues there. Say after some time, if you want to see whether your vote is stored correctly or not. So what you can do, if you know your R, then at any point in time you can go to the public blockchain where this against this G power R1, G1 power R and G2 power R plus V has been stored. Okay, so if you know that R what you have chosen, so you compute your G power G1 power R and see which row matches with this G1 power R. And then you go to the next column, which says G2 power R plus V, and you know your V, and you see whether if you compute G2 power your R plus your V, whether these two matches or not. Then you know that your vote is stored the way it's there. So we thought it's very good, but then one of my students just told them, sir, in India this is a very bad idea, because if I give you some money to vote for me, okay, then I'll give you the R. Then I can verify that whether you have voted for me. So I give money, so I have to make sure that you have voted for me. What I'll do, I'll give you the R. And I can verify whether you have done vote or not. So this we have to again think something little bit. I thought this was a good method, but now the candidates may influence the votes, and they can verify whether a person has voted for that person, for himself, herself or not. So this doesn't seem to be a very secured way of verification of one's vote after you have finished voting. But if we did allow, I could verify at any point of time whether my vote is there as it is there. And public can verify. This is publicly verified, as I told. So the basis is again very fundamental mathematics, cyclic groups, generator, discrete logarithm, and the hardness of discrete logarithm. We are using this whole notion to do this a very secured e-voting. Last part I told, I have asked you to give me a solution. How do we get rid of this privacy issue? And the first part is the most difficult part, the impersonation. Okay, so this is still, there could be, I could have, we can think of many solutions. You can just share with me. How do I stop impersonation? Naturally, as I told you, so if there could be something like a signature thing using a key, and then we have to use some cryptographic device that your identity could be proved there. And unless you can prove your identity, again, we could actually design a zero knowledge game there. So the polling officer challenges you that you prove that you are the person. This very simple thing like OTP. You have used this in OTP. OTP actually is a zero knowledge proof. So the bank wants to make sure that you are the person who is making agreed to make the payment. This is the OTP. But the problem there is again, somebody can slap me and get me mobile. and he will receive the OTP and he will just feed the OTP. So OTP is a very weak form of zero knowledge proof. But we can actually design another zero knowledge proof where the machine will play the game with me and the machine will ensure that I am the person, I am the right person. So the impersonation is not possible. So we have also designed another zero knowledge game there where the machine will play the game with me and machine will ensure that I am the right person. Okay, so you can design a zero knowledge game there also. But again, the mathematics becomes very complicated. We have to compute all these probabilities, etc. So I didn't think I'll put the slides there. So I'll kind of stop here. But if any of the issues that I pointed out, if you want to know any details, I got write-ups and I can mail it to Amik or to anybody. Okay, I hope you get the idea of how can you design a very secured, verifiable e-voting scheme. Okay, let me stop here and I'm open to questions. So Amik, you can put the questions to me and I can answer. If
Yes,
I
sir.
just look at the chat box.
So someone has a question: is a UI the UI you mentioned? Is it for the other machine or the original machine?
No, see, the machine where I vote, that machine will compute this UI. Oh, this is stored in a public blockchain. That is, there's not in the machine at all. Okay, it could be another centralized machine. I could put the UIs. Okay, these are for public verifiability. So when you compute this capital Y, capital VI, I store it in a public domain. So I would say this will be a public blockchain. So this will be another infrastructure to be added there. So after you vote, your UI and VI get stored in a public blockchain there. And that's not in that particular EVM. That's in a different framework. So you may have another machine for this public, maintaining this public blockchain.
So another question.
Yes. Okay, I get it. So now, so this is the first question. I made a presentation to the election commission, my method, and the election commission asked me this simple question, same question. Now, if a voting, how much time the voting will take? Because a lot of computations are involved there, and you think of this exponentiation, it's a not very trivial task, and the computation will be in a cyclic group domain. It's not the real numbers either. So how fast you can handle this one? So we are trying to implement it. One of my students implemented it, and at this point, I think it takes about 30 seconds. Okay, but that's that's a dedicated machine. So I would say at this point, it may take in another machine maybe even a minute or a little bit more. Okay, so this is infeasible. Now, if these computations take a minute or more, then you think of the queue to pile up against in every polling booth. So at this point, this looks theoretical. I agree, but I think we have got experts, engineers. So that's why I need engineers, not mathematician now, who can get into a nice hardware of this algorithm. If I can get this into nice hardware, which could possibly very fast. And I'd like to get a hardware chip developed on the basis of this theory, which should take in maybe 10 seconds. And I talked to some engineers. They say it's not impossible, but we didn't do the experiment yet. Okay, so I think I talked to one of my colleague at IIT Kharagpur Electronics, and he listened to it carefully and says it's possible to bring it down to a hardware chip level where these computations can be done in maybe 5-10 seconds. Then this will be feasible. But at this point, this is infeasible. The election commission is not going to accept this solution. It will take a lot of computational time. It's a good question. So,
Sir, yet another question in the chat. So, is there anything which we can give up, something which won't affect the outcomes of the result, but still will ensure a decent running time of getting the results?
Yeah. No, so see, that's why the now research going on. No, so there's this is a very nascent stage. All these e-voting stuff. But what I can do one thing. Suppose I don't know. See, let's say CMI, ISA, they don't have student union. So, but if there is a student union in a college, okay, and if you want to do online voting, then the time doesn't really matter, right? You don't queue up physically. Fortunately or unfortunately, in the good places, we don't have a student union. So I would like to do this experiment to the student union election. So you think of a Madras college, in a public college, where there are some 5,000 students, and they are electing the general secretary of the union. And you allow people to vote from his mobile or from his laptop. Okay, then whether it takes time or not doesn't really matter, isn't it? So I wanted to implement this in some union election, student election, and to verify that this really works. But still, ISI doesn't have student union, CMI still doesn't have, IITs have student union, and the other college, I really don't have much touch with them. But this could be tried. So what the time doesn't really matter. We can do actually online voting. In fact, we can even think of general election with online voting. That's maybe 10 years from today. We don't have to go to the booth at all. And in that case, there's no point of, no question of queuing up. And then we can adapt all these methods. If you can have a little more secured online voting, so people could vote from remotely. So now the other question, you have to, some UI and VI. Yes, you have to multiply all the UIs. Show me the question again.
So the question is, like, what the voting calculation might be in order of seconds, but what about the time for verification? So
Oh,
like,
no.
yeah.
See, how does one verify? So there is a public blockchain where you are putting all the capital U's and capital V's. So if I'm interested to verify that the machine is the votes are counted appropriately or properly, then I have an access to all these capital U and capital VI. What I do, I multiply all the UIs and I multiply all the VIs. Okay, so I have got this product UI and product VI with me. I know G1 and G2. Okay, I know G1 and G2. And the machine will publish in the counting stage summation Ri and summation Ri plus summation Pi. So I'll do separately G1 power summation Ri and G2 power summation Ri plus summation Pi. And this product UI must be equal to G1 power summation Ri. I can verify. And product Vi should be equal to G2 power summation Ri plus Pi. And this is my verification algorithm. It will take time, but you verify at your leisure time at home. So what is the question? What is this question?
Sir, the question is asking that whether we can use a ring instead of group to verify.
Oh, yes, I can. In fact, I normally use these finite fields for implementation because there is enough work on finite field arithmetic. But you get the idea. So you have to use some algebraic structure. That's all. So I'll tell you something. When I study in my BStat second year, I learned this abstract algebra. Okay, first year I learned linear algebra. Second year I learned abstract algebra. When I was reading this, this group, ring, field, blah blah blah, I had no idea where do I use all these things. This looked damn abstract to me. Still looks very abstract to me. All these notions of group, ring, field, etc. Generator, extension field, stuff like that. Now, when I started working in this field, every now and then I'm using this one, this abstract math concept, and this could be so realistic. Something like a voting, I'm trying to use my BStat second year knowledge. So I didn't add much knowledge after that. If you think of the algebra part here, this is my BStat second year algebra. So in CMI, if you learn the algebra, I don't know which year you learn, first year or second year. this group
Yes,
being filled.
both first and second. Like we done.
Yeah, so you don't have no clue why do I use all these things. Now here is a case in e-voting. I'm using those algebraic structures. Okay, any other question?
So there is a question that like how long should like ideally take to get to e-voting? Like you said that it may take up to 10 years. So is there any other way that we can get it faster, maybe like before 10
No,
years?
okay, I have really no idea. So this is more of political decision. It's not my decision. So if election commission, I gave a presentation to election commission, and they advised me that it should be tried out with some company elections first, the shareholders election or college student union election. So they want to see some outcome from there, and then they will just take a call. If I could influence the big companies, the large number of shareholders, say TCS, they have got lakhs of shareholders. Now the shareholders do vote. The shareholder voting, if I could adopt that, and they vote from home. So this queue is not an issue. If I could actually implement this one in some of this voting pattern, that's what they want to see first. So if I could get some Tata boss agreed to implementing this scheme into their shareholders election, that would be a case study for the election commission. I think they also want to get some confidence. As of now, I couldn't get it implemented for any real election. So this still remains a paper published in a journal.
Sir, yet another question. So what may be the reasons why it's still not being implemented?
I don't really know. I think the election commission was worried about the time taken. That's what was the worry of election commission.
So there is another question. So if
Yes.
there are still chances of being like there may be some errors while computation or something like that. So what percentage of error is like like admissible in this process?
No, see, there will be no error because this is public verifiability, that blockchain. That will ensure that if it works to this, there's no error. But if there is some error, then this public verifiability will be hampered.
Oh, okay, yeah.
Okay, so then you have to look back. Why did the error take place? This could be technical error. It could be it could be just a man-made error. But if they tally, then you know there has been no error.
Sir, I think the question was more about like what is the admissible error? So like even if I have a 5% error plus or minus, it won't matter.
No.
So is there anywhere I can relax?
No. This is has to complete deterministic. No probabilistic error. Deterministic. No error. I don't allow any error.
Okay.
I don't allow any error. So if I find any error, then there will be repoll.
Okay. No, I think the question was more of like if there is a say like a small permissible limit, say like 1% plus it's like 0.01.
No, I zero. I don't allow any error.
Okay.
I don't allow any error at all. Okay, I don't allow any error. Then if I discover any error, then I should go for a repoll.
Okay.
You know, some votes are won by very close margin.
Yeah.
You
Right.
think of some parliament election, people win by 1,000 vote. You know, there are 15 lakh voters, and somebody winning by a margin of 1,000 votes. So if I allow this 1% error or 0.5% error, this will be a complete massacre. So I don't allow any error at all.
Sir, so there was one doubt. So I read like during the when the VVPAT was introduced in 2019. So there was some permissible error. Like so, how did we manage that part? Like there was some error in VVPAT.
No. See, I'll tell you. So VVPAT, what they did some statistical testing. That's why the error came into picture.
Okay.
So see, they didn't verify all the machines. So suppose in a constituency in parliament election, there could be some 3,000 EVMs. They did not verify all the 3,000 machines. Okay, therefore took a sample of the machines and they have seen whether all of them matched or not. So there they allowed some error. So that's because that's the whole paradigm is different. If they would have verified each and every machine the VPATs, then there wouldn't have been any error.
Oh, okay, yeah. Now I got it. Yeah,
You got it, because I think the Supreme Court told you have to do at least 5% or 50% machines to be checked for the VPATs. But then from this you are trying to make an inference about all the machines. There will be an error.
right. Yeah, like we are taking a small sample out of it, and
A very small sample. That's why the error came because of the sample size.
right. So if there are any other questions, and then maybe we can conclude. Like if you have any other questions afterwards, then you can write to our email ID at tesla.cma@gmail, and we will take up with the professor and he will answer your questions.
Yes, sure. Okay.
Yeah. So
Okay.
thank you, Professor, for joining with us today. And so we will meet you all in the next lecture on 17th October, Saturday at 4 p.m. where Anup Dixit from CMI will talk about continued fractions.
Okay.
Thank you.
Bye bye.
Thank you,
Bye
sir.
bye.
Thank you very much, sir.